Okay. So, good afternoon, class. Thank you so much for those of you who made it today. I know Friday afternoon is not kind of a popular time for the classes, but thank you so much for showing your dedication coming to class. So today we're going to have a kind of fun session covering chapter 10, the last chapter of the class, talking about test of hypotheses. So I'm trying to somehow be kind of organized going through the chapter, but the thing is the chapter is pretty lengthy chapter, so it may take up to like 2.5 or 3 hours to cover the whole thing. So I need your attention. I try to give you some break in between if you need, and we hopefully can finish the whole thing all together. Okay, so feel free to pause me whenever you need and just ask questions for any part of this, because this is actually one of the important topics and concepts of the statistics you're going to learn today. And so chapter 10, as you know, is devoted to the test of hypotheses, and it's a test of hypotheses, another inferential statistical method that we're going to introduce in this class. The outcome and the result of test of hypothesis is going to be the same as confidence interval. However, it has a different approach, looking to the problems and giving us some conclusions about the problems at hand. So before getting to test of hypothesis, I'm just going to give you some introduction about it, and then we go through its procedure. So test of hypothesis is basically a procedure of accepting or rejecting an assumption or a hypothesis or a claim or a question about a population. So you have some assumption about a population. At the end of the day, you have to either accept or reject the assumption. Based on what? Based on your data, based on your analysis, and based on your conclusion of that analysis. So you either accept or reject either of these two conditions. Is that right? So the examples. I'm going to start with the first one. My friend here is going to read the first example for us from the screen.
Yeah.
Here. Medical
The medical researcher. Does coffee drinking increases the risk of cancer in the humans?
So the question is, in terms of the medical researcher, does the coffee really increases the risk of a cancer or not? Who cares, huh? We still want to drink coffee. So basically, if you really wanted to do this, what we're going to do is we can just collect the data, ask people who are drinking coffee, figure out what's the chance of cancer on those people, and so on, do some statistical analysis. So, but it's not really point of our interest, because we always want to drink coffee. But the second one could be a better example for us. Is that right? As an engineer. So it's saying that, okay, is there any difference between accuracy of two kind of gauges or not? So when I'm talking about accuracy of two gauges, I'm talking about what? Which parameter of these two populations I'm comparing with? I'm talking about accuracy of the data. So when I'm having accuracy of data, basically running the test for which parameter of the population? A standard deviation, is that right? When I'm talking about a standard deviation, I mean, okay, which one is accurate? So therefore, the test should be run based on the variance of two populations. And the third one is simply difference between two types of treatments for the people. Like business manager, when I say, okay, whether the training of the employees could increase the customer satisfaction or not. So again, you have before after kind of situation, and we're going to get the data for both. We're going to see what's the ratio of the satisfied customers. Could be difference of proportions, is that right? If I have the percentage of the satisfied customers. So therefore, we need to run a test for what? For difference of proportions of the population. So these are all questions that comes to mind, that we can answer those using test of hypotheses. However, we're going to set up a few steps that we can go through to run the test. The first one is, we have always an idea that we want to develop the problem based on this. That's the initial point. And somehow formulating this idea in the mathematics format is your art, is the main step that you have to take. So getting the idea and then convert that idea to the hypothesis that you're going to test is the key point in here. After you formula hypotheses, you need to collect data, and based on the data, you need to get some measures or statistics, and based on those measures or statistics, you will do what? You do make a decision, figuring out whether you have to accept or reject the hypothesis. That's the whole procedure I'm going to go through one more time. We get that idea, we formulate to the mathematics or in terms of hypotheses. Based on the problem at hand, we need to collect some data or sample points. We get the sample points, we get the statistics that helps us to make decision, and then once we get the decision, we may need to revise the idea. So, and then repeat the whole procedure one more time. In this class, we just go through the whole cycle once for each problem, but obviously in reality, when you have a concern in mind, you may need to repeat the test many times until it satisfies your need or concern. Okay? So, in general, we have 4 steps. I'm going to follow the exact 4 steps you can see in here for every single example or problem I'm solving here. First, I'm going to formulate my hypotheses. Second, I'm going to get my statistic to get my answer. Based on the statistic, I'm going to make decision. Based on the statistic, I'm going to make decision about the problem, and finally, I'm going to make decision about it. So, formulating, getting a statistic, specify the decision rule, and based on decision rule, we're going to make decision on the 4th step. These are the fundamental steps we have to go through for each of those test of hypothesis problems. So let's talk about the first one, how we can state hypotheses. So again, you have 2 conditions, null hypothesis versus alternative hypothesis. H0 or H null and H1. So this is a pair of hypotheses that you're going to test using some statistics, and at the end of the test, you accept one and you reject another. You cannot accept both at the same time or reject both at the same time. So this is hypotheses are a pair of mutually exclusive. That's the reason we just cannot accept both of them, because they are what? They are mutually exclusive and collectively exhaustive, meaning that they are covering all of the possible options that we have in front. And based on those hypotheses, you're going to run the test. One statement or the other must be true, but they cannot be true at the same time. And these statements are hypotheses because truth is unknown to us. That's the reason we are not saying these are kind of statements. These are hypotheses, because we have some assumptions. We collect data. Based on the data, we verify which of those assumptions is true, or which of those hypotheses is true. However, there's a subtle difference between these two. So you may say, okay, it's pretty easy. Okay, I have a problem. I can say, okay, this is the first one, this is the second one, run the test. However, the important part of any test of hypothesis problem is formulating the stating hypotheses, because it's going to totally change the outcome or results that you're getting at the end of the problem. So, what are the differences? So, the main effort usually goes to reject the null hypothesis. I will tell you why. So, I give you an example, and based on an example, we can see what you can do in order to formulate a hypothesis. Assuming that the police arrested a guy, Mr. A, and it's been kind of assumed that he's a guilty person. So what people do, what the judge does actually in most cases, they start collecting evidences, is that right? Information about the incident, is that right? Asking witnesses. So they have a bunch of information that they collect, and the judge makes decision based on those evidences or information that they are getting for that case. Is that right? So, excuse me, can you just sit somewhere not close to the camera, because I've seen people unplug the whole thing, unplug their laptops, and they that's fine. Just wanted to let you know this is something kind of that's not happening. So I'm talking about a person who's guilty. So I'm going to have 2 ways to run the test. The first way is saying that Mr. A is a guilty person. Oh, sorry. Mr. A is an innocent person. or is not, yeah, is and the alternative saying that Mr. A is guilty. So, after all of the investigations and all of the data gathering and information gathering, the judge makes decisions. Okay. At the end of the day, these are the two different types of decisions you may see. The first decision could be what? Concluding that there is no evidence that he's a guilty guy, so we can say he's an innocent person. Is that right? So there is no evidence showing Mr. A is guilty. So, and the second one is based on the gathered data, Mr. A is guilty. So again, we accept one or the other. So, if you wanted to pick which one of these statements as a stronger statement, which one do you pick? And which one you have more confident based on your conclusion results? Which one you're more confident about by your decision results? Yes.
I'm more confident that he is guilty because there is evidence that he's guilty rather than there being no evidence.
Exactly. So this is a stronger statement. So if I get some evidences or witnesses showing that he's done something wrong and he's a guilty person, so I'm making a decision based on some evidences that I have on hand, and then I'm kind of somehow confident about my decision. However, in this case, I'm not having enough evidences or information or data that tells me that this person did something wrong. So I have no choice unless I let him go. Is that right? If I do more investigation, if I have other people, if I have some other sources, could somehow show he's done something wrong and I can send him to jail. But at this point, based on the collected data, based on whatever I have right now, I have no choice unless let him go, and assuming that he's not guilty. What I'm saying that he is not a guilty person. But it's kind of hard to say that he's an innocent person because what? Because he had done something wrong that he's been arrested. Is that right? So we were kind of suspicious about him that we arrested him. And at the end of the case, we found out, okay, you're not having enough evidences to showing that he is a guilty person. So therefore, we call the conclusion from the second alternative hypothesis, or H1, as a strong hypothesis because its conclusion is much stronger than its null hypothesis. And this one becomes a weak hypothesis. So, now it justifies the first sentence in here, which is saying what? The efforts will be made to reject the null hypothesis and conclude the alternative. Because if I reject the null and if I conclude the alternative, I'm making a decision based on confidence that I'm getting from my data and my statistics. So therefore we say, okay, we are rejecting with certain level of confidence. But if I do not reject, we never say we accept. What would you say instead?
Fail to reject.
We fail to reject the null. Saying that, okay, at this point, we are not able to reject it. But we never say we accept the null hypothesis. So the decisions are these two. First, either rejecting the null and concluding the alternative, or failing to reject the null. So we never say we accept the null. In this case, we never can say Mr. A is an innocent person, we just can say he is not a guilty person. Or we fail to show he is a guilty person. Does it make sense? So this is very important on terms of way that you're stating hypotheses and putting those things to form this pair of hypotheses here. So if H0 or H null is rejected, we tentatively conclude H1 to be the case. And if null is sometimes null is sometimes called to be maintained hypotheses, and alternative or H1 is called to be the action alternative, because action may be required if the rejected null in favor of the H1. So the other names for those is like we call it the null hypothesis as a maintained hypothesis, and H1 as the action hypothesis. Give you a kind of industry example. I have batteries that they should have a lifetime of 30 hours. So I'm saying that the null batteries have average lifetime of 30 hours. On the second one, batteries do not have, or they have a battery's lifetime of less than 30 hours. Is that right? Yeah. So if I conclude the first one, do I need to take any action? If I conclude that the batteries have the lifetime of 30 hours, do I need to take any action? No, I'm satisfied with the performance of batteries, so I do not need to take any action, so I maintain my condition. But if I conclude the H1, meaning that the batteries have a lifetime less than 30 hours, then I have to check my procedure, I need to somehow improve its quality, and something like this. So therefore it's called an action alternative. So if I again conclude the null, I do not take any action because I'm satisfied with the performance. But if I conclude the H1, in most cases you have to take an action and somehow bring some changes to the system. Can hypothesis be proved? The thing is, we cannot accept the null hypothesis, we can only fail to reject it. And this is one of the important things that you have to consider when you're making decision about this. So I'll just give you an example about this thing, the criminal trial case, but the same thing is for drug testing or anything like this. So we say, okay, for the drug testing for an Olympic athlete, so no illegal steroid use or illegal steroid use. So if he found there's something in his blood that's showing that there is evidence of the drugs, therefore we have a proof for this, is that right? And if he cannot find anything else, so he may have used something that we are still not able to discover, is that right? So we don't never know. But if you have something that shows, okay, he has used some illegal stuff and illegal drugs, so there we can say, okay, illegal steroid is being used. So that's the main way that we have to form the hypothesis. I don't want to talk about this one that much, but basically for any test of hypothesis example or case, we have 4 different conditions. What are the conditions? I have it on my slide, so it's better to talk about here. So these are decisions that we make. These are reality, is that right? Everything is unknown to us. So we never know what's happening in reality. We're just making decisions based on data and the statistics. Is that right? If in reality, null be false, meaning that the person is a guilty person, on that example. Null becoming false means what? The person is a guilty person. And if my decision is saying that I'm rejecting the null, I have a good decision, is that right? He was a guilty person and also rejected the null, meaning that he was a guilty person. I'm fine. However, in the same case, if the person be guilty and I decide, let me discuss this first. But if in reality the person be not guilty and be an innocent person, but if I decide that he's a guilty person, I had a bad decision. Is that right? He was not innocent in reality, but I ended up saying that he's a guilty person. I'm sending an innocent person to the jail. Therefore, this is the first type of error. So what's the first type of error? It's actually a probability of what? Probability of rejecting null, where null is true or correct. Is that right? The null was correct, meaning that the person was not guilty, but my decision was based on rejecting the null. That's the first type of the error, which is the probability, or alpha. The second type of error occurs when when null is false, meaning that he's a guilty person, but I ended up saying that he's not a guilty person. I failed to reject the null. So in that case, I also made the second type of the error, which is beta, and it's actually called false negative. So it's basically the probability of accepting the null where given that the h1, h0 is false. So these are two different types of errors. You cannot minimize both at the same time. If you decrease alpha, the whole point is decreasing the error, is that right? So if you decrease alpha, beta increases. And the same thing, if you decrease beta, alpha increases. But again, I'm not going through the whole details of those things. But feel free to search about it. It's a pretty cool topic though. But it may need at least a session to discuss, okay, how these two are related and how we can set them up. There's also something that's called the power of the test, which is based on 1 minus beta. So the lower the beta is, the more powerful going to be the test. So there are some curves being drawn based on this beta value. And it's actually a pretty cool topic though, but our focus in this class is just going to be on beta, alpha, which is the significance level of the test. It has the kind of the same meaning of confidence level of, this is error here, so 1 minus alpha is what? For the confidence interval, we're saying that the 1 minus alpha is the confidence level. Here we are instead of saying the confidence level, we say significance level, which is alpha, or basically the error of the test. Okay, but alpha is the same alpha we had for the confidence interval. If your confidence level is 95%, your alpha is 5%. Is that right? The error rate is 5%. So therefore we call the alpha the level of significance, the error that we're going to have for our test. These are some general introduction about the test. We also going to have 3 different types of the test. That's going to be the last part of intro. Then we go through the examples, and you're going to see how cool that test of hypothesis is, and hopefully you're going to enjoy the topic. Okay. Depending on the types, depending on the cases that you are dealing with, you could have 3 different types of the test. The first one is called the two-tailed test. I'm testing mean for a certain value of mu 0. So I'm saying, for example, again, I'm going to say the processing time of my assembly line is 25 minutes per item. So I want to see whether this processing time is 25 minutes or not. So my test is what? H null, mu equals to 25. Alternative, mu is not 25. So mu is actual parameter. Mu naught or mu 0 is what? Is actual value that you're testing. So this is the specific value, but this is the parameter that you're testing. So this is a two-tailed test. Why? Because I'm not interested of the upper bound or lower bound. I'm not saying whether mu is less than 25 or more than 25. I'm just saying whether mu is or not is equal or not equal to 25. Therefore, I have a two-tailed test. How can I figure out this is a two-tailed test? For all of the tests, in order to determine the type of the test, you have to look at the symbol on the alternative. This is my alternative. My symbol is inequality. And when you see inequality, that means it's a two-tailed test. When I have a two-tailed test, I have half of the alpha to the left of the curve, the other half to the right of the curve, and that's it. Therefore, it's a two-tailed test. What about the other type of the test? We also could have a left-tailed test. For example, I'm saying that my patients in my system, in my hospital, should have waiting time less than 30 minutes. If it's more than 30, this is the other case. Sorry, my bad example. This is left-tailed test. So I'm saying I have batteries, again, same thing, that these batteries should have a lifetime more than 30 hours. More than 30 hours, if it's 40, 50, I'm fine with it. But if it's less than 30 hours, I have to somehow fix it and improve the quality. So my rejection area should be the lower side of the curve, where the mean time is less than 30 minutes, 30 hours. Is that right? So whenever you have a concern, whenever you have an issue, or whenever you have a question, you always have to put that question into the alternative, not to the null. So here I'm saying what? I'm saying that the quality of batteries should indicate that batteries have a lifetime more than what? 30 hours. So if it's less than 30 hours, I have to reject my batteries. So I'm saying that mu is less than 30, and the opposite of this goes to the alternative, to the null hypothesis. So therefore my rejection is what? Is the lower side of the curve. If mean is less than 30, I have to reject it. So this is called what? A left tail test. How we can figure out this left tail test? Again, look at the alternative, look at the sign, it's less than sign, therefore it's a left tail test. And the same thing for the right tail test. Our error is all the way to the right of the curve. In this case, having mu more than a certain value should lead us to reject the test. For example, the waiting time of patient in a hospital. We are saying that our patients are satisfied as long as they are getting service within the first 30 minutes of their arrival. If waiting time is more than 30 minutes, we have to somehow improve the service quality. So which side is kind of a bad situation for us? When mu is more than a certain value. Therefore, again, I put my concern, I put my question to the alternative. I'm saying, okay, if mu is more than 30, this is my alternative. I have to reject the test. And the rest of that, which is the kind of opposite of this, goes to the what? To the null hypothesis. So depending on the type of the question, depending on the type of the problem, you either should have a two-tailed, right tail, or left tail test, and you have to figure out before you solve the problem. That's the reason I'm telling you the way you're going to formulate the hypotheses could hugely impact the outcome and results of the test. In some cases it's two-tailed, in some other cases right or left tail test. Okay. By having this introduction, we are able to start the first test. Again, we always look at the direction of the test is indicated by H1, not the null hypothesis, folks. Please pay attention to this. So, once you get the rejection region, like the whole curve is called rejection region. So once we figure out it's a left tail or right tail or two-tail test, we have our decision rule. This is our kind of guideline which helps us to make a decision. I will calculate a statistic. If my statistics falls within the rejection region, like in here, or in here, or in here, or in here, I have to reject my test. Otherwise, I fail to reject it. That's pretty simple. So you have a rejection region, which is your guideline, and you find a statistic. If your statistic falls within the rejection region, you have to reject the test. Otherwise, you fail to reject it. And this is the whole procedure we're going to do in here. So we're going to repeat the whole procedure many times for many examples, and I'm sure you're probably going to get all of those steps one by one together. So let's just start with performing a test of hypotheses for one sample for one sample mean when sigma is known to us. We're going to have the same type of test as we have for confidence interval. One sample mean with known variance, one sample mean with unknown variance. Two means, known variances, unknown variances. Proportion, difference of proportions. Variance, ratio of variances. These are all different types of tests we're going to cover today in here. So, any question before I start the first part of it? Anyone? Okay, cool. So, these are the first two tests we're going to discuss today. The first testing mean when sigma is known, I'm going to use what? Z distribution, and when mean is not unknown to us, you're going to use T distribution. Good. For all of these tests, I'm going to give you a statistic. Most of those statistics been covered before in chapter 8. Nothing new. The whole thing is, the only new part is just the procedure of the test. You remember when you wanted to find the probability of x bar, what was the z for the x bar? X bar minus its mean, which is mu, divided by its standard deviation, which is sigma over square root of n. That's the same thing. I'm going to get my z cal. I'm defining my z cal for min based on the same function, the same formula. X bar minus mean of x bar over standard deviation of x bar, which is x bar minus mu 0 over sigma over square root of n. What's the mu 0? Mu 0 is the mu that you're testing for. You're saying, okay, mu is 30. You run a sample, you get the x bar of 27.5. So then x bar is from sample, mu 0 is the mu that you're testing, and then you can form the calc to run the test. Pretty simple. So the only thing you have to know for any single test is just what's the appropriate calc to use. It's a z calc, t calc, chi-squared, f calc. What's the calc that we're going to use to run the test? And then you're good to go. I'm going to start with the first example, and so let me just fix this part of it. What happened? Okay, pressed cancel, huh? Oh, okay, oops. Yeah, this one. Oh, fuck. Okay. That's good. It's good now. So, my friend Irfan can read the example for us.
The Hammermill company produces paper for laser printers. Standard paper width is 216 mm or 8.5 inches. Suppose that the actual width is a random variable that is normally distributed with non-standard deviation of 0.0230 based on the manufacturing technology currently in use.
Okay, so I'm going to stop here. So, we're talking about what? We're talking about a paper. We should have the quality of 260 millimeter for the width of each of the papers. Pretty tiny, is that right? So this is what? This is the width of the paper, and therefore this is the standard of the industry, that the company should produce papers with the same standard. If the width be more than this, they're going to stock in the printer. Is that right? So they have to make sure that the papers that they're producing are within the standards and also having a kind of a good thickness that can go through the printer. Okay, this is a standard. It's not talking about a company yet. And we know that based on this standard, also the standard deviation for width of the paper is 0.0230. This is the other element. So mean of 216 and what? The standard deviation of 0.023. This is what we have to see from the paper width. Okay, move on.
Variation arises during manufacturing because of slight difference in the paper stock, vibration in rollers and cutting tools, or wear and tear on the equipment.
So these are the possible causes, possible different ways that you can see some changes on the paper thickness through the process.
Suppose that a quality control inspector chooses 50 sheets at random and measures them with a precise instrument, obtaining a mean x bar equals to 216.0070 mm.
Okay, so the company is concerned about the quality of the papers. So what they do, they have to provide some data and they have to do sampling. They got 50 sample points, and after sampling those, if they found that the x bar or the average width of the papers is what? 216.0070. Pretty precise.
Using a 5% level of significance, alpha equals to 0.05, Does this sample show that the product mean exceeds the specification?
Okay. So we are concerned about what? We are concerned about the width of the papers not being greater than a certain value. Is that right? And that certain value for me in this case is
007.
anybody else? So what I'm testing here, I'm testing mean. Is that right? And I'm testing mean which is what? Which is the standard paper width of 216 millimeter. That's not thickness, that's my bad. It's kind of width of the papers. So I'm saying that X is a random variable of the paper width, and X is normally distributed with unknown mu, but we know with sigma has a sigma of what? 0.023. I'm talking about what? The company's paper, not the standard. We don't know what's the mean of the papers being produced by the company. Therefore, we don't know what's the mean. So, but what we can say is, so we can say the test that we are running is based on these two hypotheses. Mu should be within the standard, and the standard is indicating that the paper width should be 216,000. So if the papers produced by the company are within the standard, we are happy. Otherwise, we have to check the procedures. So my question is, being less than is important for us, or being more than 216, or being exactly equal to 260? Which one is more is point of interest here?
Equal to.
What?
Has to be exactly.
Exactly 216. Anybody else?
Has to be less than or equal to.
Should be less or equal to?
Equal.
Anybody else?
Equal.
Look at the last part of the problem. Last sim. What does it say?
Exceeds the specification. That means it should be less than or equals to.
Left tilde does.
Okay.
Yeah.
The problem is saying whether the mu is more than 216 or not, is exceeding 216 or not. If it's more than 216, there's something wrong with it. Is that right? Is that right? Because again, it's going to stuck in the printer, all this stuff. And it's saying so what? It's saying that test whether the mean is exceeding the specification or not. As I mentioned earlier, the point of interest or the question or the claim or the concern that we have about a problem always goes to the H1. So I'm saying that is mu more than 216 or not? So again, I always put the whole test, I always put the claim or the question of the problem to the alternative, and I put the opposite of this to the null hypothesis. That's my first step. I formulated my hypothesis. Is that clear, folks? The second part, getting calc. Z calc for this test equals to Z of alpha over 2. My alpha is 5%, but I need to figure out, okay, so my Z calc, is X bar. So based on the test, we need to run it, we have to get the calc. We got the sample data from the process, and we found that X bar is 216.0070. This is X bar, and this is from sample, folks. And I'm testing this against the true population mean, which should be 216. This is the mu that we are testing. So should be minus what? 216.00 over sigma, which is 0.023, over square root of n, which is 50. The answer is
2.152.
2.152. Great. I'm done with the second step. The third step. Specify the decision rule. DR. I'm using an approach which is called rejection region method. This approach is called RR, rejection region. Depending on the type of the test. What's the type of the test in here? This is a greater than sign, therefore this is a right tail test. Meaning that all of my alpha is to the right of my curve, which is 0.05. Am I right? And z of alpha is what? Can anyone tell me? Z of 0.05? 1.64? 5. So, on the fourth step, I make decision. My z-calc, 2.15. Where does it fall? 2.1, this is the calc, 2.152. Is it in the rejection region? Yes. It falls to the rejection region. So we're going to say since z-calc equals to 2.152 falls in the rejection region, the conclusion is what? Reject null, meaning what? The paper does not meet the specification, and we need to check the processes and take action. Yes.
I've come across a few of these similar problems before, and I've always found the idea that in industry that they're looking for the mean of this sort of thing, and why they're not looking for the standard deviation for like this specific sort of circumstances where you're trying to find and they're like you're looking for the average versus the standard deviation of like how much it varies, like
We're going to have a test for variability later on.
Yeah, and I'm just wondering for this specific sort of a question where they're trying to make sure that it stays within a certain boundaries, that they're obsessed with finding the actual mean.
That's a good question. So if you really are concerned about the boundaries and the specifications and all the variability of those things, you have to run a test for a variance.
Yeah.
So based the same thing we did in here for mean, you have to get estimation for variance using S squared and run a test for a variance which we're going to cover later on. So the mean point is one point of interest. Like we also like knowing what the mean is. This could be one of the questions that we have to ask. Also, as you said, the tolerance or variability is other questions that we can ask on top of it. But at this point, I just wanted to show the interest. I just wanted to show, okay, we're running tests for mean and how we can run the test for that. Well, that was a good question, though. Okay, great. Any other question? So, that was one way and one approach to solve the problem. This approach is called a rejection region method. No cell phone in class, folks. Please. So, the thing is, what we're going to do here on the other approach, we have to figure out what's the probability related to the z-calc. So, in this case, what we have done, we defined the hypothesis, we got the calc, and we defined the rejection region based on what? Based on alpha. And then I compare these two numbers together. On the other method, we do the other way around. What we do? We get the calc, we find the probability of this, and we compare the probability of this with alpha. Does it make sense? So in this method, for rejection region method, I had alpha, I found its z value, and compared z's together. On the other way, I can find the probability of this, which is a p-value, and compare it with alpha. And therefore, the second approach is called a p-value approach. Pretty probability of the z-calc. So, what's the difference? Difference for the first step is nothing. Exact same thing. So, I can keep the first two steps if I want to use a p-value approach. But now I'm going to say this is a p-value approach. How we can find a p-value? Based on two things. Remember that. You ready? First, which one is first? This one is first. First is based on the z-calc value. Second thing based on the type of the test. So, I know I'm using a normal distribution. And my z-calc is what? This is z of 0. Z-calc is 2.15. Do I have a right tail test? Yes. Area to its right gonna be your p-value, folks. Pretty easy. Now, all of you have to look at the z table. For z of 2.15, and tell me what's the area to its right, not to its left. Because this is area to its right. So, P of z more than 2.15 is what? 1 minus? 0.942, and this is 0.0158. Is that right? This is my p-value, and now I can make decision. This is a probability value, and on decision making, for decision, we make decision based on this. You actually can see on the bottom of your handout. It says what?
P is low.
When null is when p is
low.
okay.
H
Null.
is going to accept it.
Okay, thank you so much for destroying my sentence. So if p-value is low, null gotta go.
Oh.
Okay? Which is pretty simple to memorize, alright? Saying that what? It's saying if my p-value is smaller than my alpha, I have to reject the null. Is that right? But it's kind of easier way to memorize it. So decision is like this. If p-value is less than alpha, we reject the null. If p-value is more than alpha, we fail to reject the null. What happens in here? My alpha is 0.05. My p-value, which is 0.0158, is less than alpha of 0.05. Therefore, what we do? We reject the null. The same conclusion, but different approach. Is that right? Bless you. So, again, what we did in here, the first two steps are identical to the rejection region method. But from the third step, instead of getting the rejection region, we get the p-value, and p-value is basically the probability of your z-calc. And on the last step, you just make decision comparing alpha and z and p-value. If p-value is less than alpha, you reject. Otherwise, you fail to reject. Okay? So, the question is, which of these methods is more convenient to use? If you wanted to pick one, raise your hand and answer my question.
This p value,
Why p-value?
because here we need only the z-calc value, and from the hypothesis writing h0 and h1 we can find the direction. we need only these two things.
So for a rejection region, we also need zcalc and the type of the test. That was pretty easy. So what's the difference?
First one is easy.
Say that again.
First method is easy
First method is the easier one. Why?
because we will anyway find out zcal for both of the methods, and we just have to know the critical value
So like,
if we can remember.
I don't see the difference from your explanation though.
But you have to find the probability in the second method as well.
No. On the other one, I had the probability, I had to find the z. And this one, I have the z, I have to find the probability. No not a big deal, not a big difference. Anybody else? So let me change my question. If I give you the same problem with another alpha, like saying alpha of 0.1, in which one you can give me the results pretty quick and fast?
Second.
Well, why second one?
Because in the first method we can't really remember the critical values for all the confidence levels, because we are more used to 95% and 95%. It's easy to remember some critical values, whatnot.
So different people have different preferences, is that right? So someone say, okay, my alpha is 0.001, some others say my alpha is 0.05 or 1%, 10%, I don't know. If you change the alpha, you also need to update your rejection region, because the whole rejection region is based on alpha, is that right? So if I change my alpha to 0.1, if I wanted to use the rejection region, I had to construct the whole thing, find the new z's, compare z's together. But if I go with the p-value method, if I say, okay, now alpha is changed to 1%, what do you tell me? If I change alpha to 1%, 1%, is this one less than 1%? No. Then we fail to reject the null. It's pretty easy comparison, is that right? So therefore, p-value is a standard way of running the test of hypotheses, because you can easily make decision by comparing your alpha with the test p-value, and if p-value is less than alpha, you reject the test. If p-value is more than alpha, you fail to reject the test. You don't need to reconstruct the whole rejection region based on your alpha, compare these together. You can directly compare probabilities together and make decision. I'll give you a bonus point. So this is the main thing. So when you use R, MATLAB, Minitab, they all work based on the p-value. Also, if you remember, for the goodness of fit test, we're getting a p-value, and we could easily make decision. An alpha of 5% is a typical alpha. So if alpha is not given to you, you can assume alpha is 5%, unless indicated as a different value. Okay. Going back to the p-value method, I just want to mention that there are other two types of the test. If p-value is a right-tail test, like as we had, p-value is to the right of the zcalc. If test is a left-tail test, p-value is to the left of the zcalc. But if it's a two-tailed test, you get one zcalc, but here you have half of alpha to the right, half of the alpha to the left. Therefore, the same thing happens to the p-value. Half of p-value is to the left, half of the p-value is also to the right. You find one of the probabilities and you have to multiply it by 2 to get the whole p-value. So I'm going to also show another example for this two-tailed test based on mean or mu. Okay. I have to ask you to read all of the examples today.
Okay. A sample of 40 sales receipts from a grocery store has X bar is equals to $137 and sigma equals to $30.2. Use these values to test whether or not the mean sales at the grocery store are different from $150.
Thank you so much. So, here I have X as random variable of sales. And can you tell me what's the type of the test in here? Why to tell, why not?
Because they are just asking if the sales are different from 150.
Exactly. We're just saying whether the sales is different than 150 or not. Not more than or greater than or less than or less or, I don't know, something like this. So, X again is a random variable of number of sales or sales price. Sales receipt. Sales receipt. And X has a normal distribution with unknown mu, but a standard deviation of
30.2.
30.2. So we got a sample of those. We got a sample of those, and from sample we found that X bar is
137.
137. So the test that I'm running is saying that whether the mean is 150 or not. This is a two-tail test. Okay. This is first step. Second step, getting calc. I'm using zcalc. X bar 137 minus mean 150 over sigma 30.2 over the square root of n, which is how many? 40. Zcalc is 2.722. So I'm going to use both methods here. First, rejection region. Curve is a normal curve. Zcalc is a 2.72. My bad, sorry. This is rejection region is based on alpha. So half of the alpha to the left, the other half to the right. Why half of alpha? Because this is a two-tailed test, folks. What's my alpha? It's not given. Well, I assume it's 5%. If it's not given, I assume it's 5% alpha. Therefore, this is what? Z of 0.025. This is Z of negative Z of 2.0, negative Z of 0.025. Is that right? What's the Z? 1.96 and negative 1.96. And the last step, make decision. What do you conclude? Since Z calc equals to 2.722 falls where? Are you sure about this Z calc?
Sir, it is minus 2.7.
Do you want a negative 2.72? I need one of you guys recalculate this again. So negative 2.72, huh? So since zcalc is negative 2.722 and negative 2.722 falls where? Here. Is that right? So since it falls within the rejection region R, what we do? We reject the null, meaning that the receipt mean is not, the sales average is not 150. Do you have the alpha in your problem or not? Can you calculate this one more time? So I want to write the rejection p-value method here, which you can find it's on the second part of the problem. Is that right? On the other page. No? Do you have it? Yes. Page 6. You solved that?
My friends.
It's minus 2.722.
Say that again.
It's minus 2.722.
Okay, great, thanks. So if I want to use the p-value approach, what do we do? What does your friend say?
This side p value by 2 and this side p value.
Okay. I have it's same curve, normal curve, is that right?
Yeah.
Half of the p-values in here, other half of the p-values in here. But again, how we determine the p-value? Based on z-calc. Negative 2.722, area to its left. What's the area to the left of this? P of z less than negative 2.722 is, or negative 2.72 is? 0.003. This is 3, folks. And therefore p-value is what? 2 times this. Why 2 times this? Because the two-tailed test. 0.006. Again, if it's a left tail or right tail, we do not multiply by 2. We just multiply by 2 when it's a two-tailed test. And finally, we make decision. P-value, which is 0.006, is less than alpha of 0.05. The same conclusion. E, reject the test. So from now on, you have to be able to solve all of these examples using both methods, rejection region method as well as the p-value method. Questions? Yes.
In the third step, why double 0, 0 point?
Okay, good question. Because this is a two-tailed test.
Oh, two-tail.
If it's a two-tail, we multiply by 2. If it's not a two-tail, we just
If
leave
right
it.
or right.
No, we do not multiply by 2, yes. Okay. Is it clear, folks? Great. So, when the sigma is unknown to us, we're going to do the same but using t-distribution. Therefore, it's called t-calc. And in t-calc, we have x bar minus mean over what? S over square root of n. And our t has a degrees of freedom of n minus 1. But the same procedure, the same structure, nothing else. So we start with this example number 3. And we're going to talk about Dunkin' Donuts. How's that? I'm not a big fan of those, but
Yeah. In addition to its core business of bagels and coffees, Dunkin' Donuts also sells hot coffee for non-coffee crowd. Customer search shows that the ideal temperature for hot chocolate is 142 degrees Fahrenheit. That's hot, but not too hot.
so you can sue them if it's too hot, huh?
A random sample of 24 cups of hot chocolates is taken various times, and the temperature of each cup is measured using an ordinary kitchen thermometer that is accurate to the nearest whole degree.
So, yeah, let me just go there. So, we basically want to see whether the Dunkin' Donuts is keeping the hot chocolate hot enough or not. So, and we got the data. These are the sample data. And we found that we're going to run the test to figure out whether the mean differs from 142 or not. What's the type of the test? A two-tailed test. I'm just seeing whether mean is 142 or not. I gave you the data. What do you have to do? Find its mean, find its standard deviation, run the test based on the t-calc and t-distribution, just rejection region method. We are not using p-value for this example for now. So all of you, please go ahead and start calculating those stuff. So, Ix has a random variable of hot chocolate's temperature, is that right? And what's the distribution of my X? Normal with unknown mu, but an unknown
So T.
sigma. Is that right? None of them are given to us. Therefore, we are using T distribution. So, I formed the hypothesis. Now, mu is 142. Alternative, mu is not 142. Because it's just saying differs, meaning that it's a two-tail. It's not saying it's greater than or less than. It's just saying whether it differs or not. So it's a two-tailed test. So, data tells me what the X bar is and what's the S. Tell me.
141.37.
141 point
37.
and S.
1.99.
1.99. I'm going to say 2 if you don't mind. Is that okay?
Yes.
Thank you. So, I'm going to forward my T-calc. Is X bar 141.37 minus mean that I'm testing, 142 over S, 2 over the square root of 16?
No, it's 24.
24. The T-calc is based on 2, folks. Give me the answer based on 2. You got it?
No.
Your friend? No?
But it's different answer.
Oh, okay, he did it wrong, huh?
Maybe.
Okay. Can you just verify the X bar and standard deviation for me here? He got the wrong different mean and standard deviation for those?
Actually, he has used 1.99.
Okay.
Not 2.
Minus 1.54.
What you got for this?
Minus 1.54.
Minus 1.5?
540. Yeah.
40. Great, thank you. I go to the third step, forming my rejection region. Distribution is a T distribution.
Yeah.
Type of the test, two-tailed test. Alpha,
0.00. No, it's alpha by 0.
0.1.
what? 1%, 10%?
Yeah, 0.10.
Yeah, but alpha by 2 is 0.0.
So this is what? 0.05.
0.05.
This is what? T of 0.05 and degrees of freedom?
23.
23. Negative T of 0.05 and 23. What are T values?
1.71.
1 point?
714.
Negative 1.714. Make decision now. Negative 1.54 this is my T calc. So since
That's not fall into the
yes, since the T calc does not fall within the rejection region method, rejection region, what do you conclude? We failed to reject the null. Is that right? Which means what?
The mu is 140. Enjoy the hot chocolate.
Yes. Enjoy your hot chocolate. So their core business is mainly donuts, is that right? Not coffees, but maybe all, I don't know. So you also see how you can get this done for the p-value using Excel. You can also use R. For the p-value thing, Kirtan, sorry, Mohit, I want you to help me with the R function for T distribution. Okay? Yes. So how can I get it done, folks? By using p-value. Are you done with this? No? Not yet. Yes. So do you want me to explain?
No, I'm.
You're just writing. Okay, go ahead. I'm just going to talk with people. So, how can I find a p-value? We are not able to use table because we don't have that much p-values from the table. Is that right? It's pretty hard to find it. I can somehow estimate using t-table. I don't want to go through this because it doesn't make sense. Like just an estimate. So, if I want to use the p-value, I have to get my cap, negative 1.54. Find the area to its left, and then multiply by 2 because it's a two-tailed test. So, Mohit, I need this. Area to the left of t negative 1.54.
Sorry, what do you need?
I need area to the left of t of negative 1.54. T distribution. Are you done, my friend?
Yep.
Great. So I'm changing my approach to the p-value approach. I want to ask you to do it by yourself again at the home when you have access to R. I'm going to give you the function as well. So here, based on the p-value method, I'm getting the probability to the left of negative 1.54 and multiplied by 2 because it's a two-tailed test. This is half of the p-value. This is the half of the p-value. So I'm looking for the p of, this is the probability of t be less than negative 1.54. The function for that in R is, Mohit? PT, that's it?
Yeah.
Okay, pretty cool. So it's x is x or q?
If it is Q, it will give Q.
Q equals to negative 1.54. That's it?
Yep.
The answer is?
I'm getting an answer.
Sir, here the answer is written 0.069.
No, I'm just going to get it from R because I want to ask people to do it by themselves. Yes.
What's the standard T distribution?
It's like T is TA, mean of 0, standard deviation of 1, nothing else. Just. Do we have the PT function in R?
Yeah.
Let me see that. So you're getting the.
I'm not sure that's the right.
Oh, degrees of freedom. 23, huh?
Yeah, that is what I was asking.
.068. Do you have the same number, my friend?
0.069.
Okay, I have a better answer from R. So, the function in R is this, folks. Q of 1 negative 1.54. And what's the argument for the degrees of freedom? df?
Yeah.
And df equals to 23.
Yep.
And you will get the answer equals to
0.068.
0.068. This is half of my p-value. Is that right? So the p-value is 2 times 0.068, and the answer is, Mohit?
0.136.
0.137. Okay. So I make decision. P-value is, which is 0.137, is more than alpha of 0.1. Then I fail to reject the test. Does it make sense? So you can easily run the same test by yourself. Lab 5, which is going to happen next Friday. Going to cover those things. Again, it's optional lab for you. If you your optional class for you, if you don't want to come, you can watch the videos. But it's going to be short class, maybe less than an hour. Not that long though. So, any question? That was the all of the tests for the mean. We can also do the same thing for two means. Yeah. Oh, yeah. One thing. It's very important. So, as I said earlier, there is no difference between confidence interval and type of test of hypothesis. If you want to answer the same question using using confidence interval, the significance level is 90%. Is that right? And when you get the confidence interval using the equations from chapter 9, you'll get a confidence interval between 140 and 142.07. What do you conclude? This range includes 142, therefore we can say the hot chocolate has a good temperature. The same conclusion as we got from the test of hypothesis. So one more time, if I consider the confidence interval for the same problem, I'm getting the range of 140.6 and 142.07. Since this range, as you can see on the graph, includes 142, we fail to reject the test. We can say mean could be 142. So that shows the relevance of test of hypothesis and the confidence interval. Okay. Also, if you're interested to know how to use Minitab, I have a slide in here, but I believe you prefer to use R because that's the main software for us to use in this class. Do you need a break?
Yeah.
Yes.
I have a specific question.
So I will give you 7 minutes break up to 3. We come back with some other cool problems, and maybe I believe we have 6 more problems to do, and that will be done. So we should be done by 4:30. Yeah. So yes, what's your question, my friend?
Okay, so there's so I was working, and there was a problem that they were trying to change distributors, and the product they were trying to measure was like these really tiny metal plates that their distributor was giving them, and that their choice of changing distributors was based off of the mean value of the width of those distributions. And then they would say, okay, if they were testing if the mean was the same as the current distributor, that which just didn't make any sense to me personally, because like you're trying to, there's upper and lower bounds of what are acceptable parts, acceptable width of this method, and so and you're trying to get like 95 or whatever, however many percentages that you want out of that, stay within those upper and lower bounds. And they were just testing the mean to make sure that the mean was the same as their current model, and didn't even, like, they don't know variance, they don't know standard deviation. They were doing two-tailed t-tests, and and so I was.
Yeah, this is something we are saying that the conclusion we are getting is just statistically significant. You cannot really compare means together, or that's the reason we get the sample data. If I wanted to compare means, like, I could use point estimations.
Yeah.
The main reason we are getting samples is because we're going to have more evidences, more data, and better estimation with lower error.
Right.
Like, all of those are based on what? Based on the sample size. The larger sample sizes, the lower going to be the t-value. The larger going to be t-value. When you have a larger t-value, you have a lower error.
Yeah.
Does it make sense?
Yeah, I'm just thinking with the process that they, like, if you're looking at two data sets, if you're looking at two sample sizes and you're trying to prove that that within the next sample size falls within the upper and lower bounds as the other sample size does. I think variance should almost certainly be like the test that they should look at if you're looking at upper bounds and lower bounds of material. instead of mean. Like,
So, okay, I know what you're talking again. We're gonna have a test for lower, like you have, based on the same data, you can run the test for the variance and variability.
right.
And that tells you if you're concerned about that thing, you can consider both at the same time. But this is about, also somehow this stuff mean is dependent on test of variance. Because if you do not know what the variance is, you have to determine variance and run a test for the variance to make sure that the variance is the right true, has the true value, sorry. And then, based on that true value of variance, run the t-test for mean.
So that process was completely
I know. No, somehow that is true. Like this is theoretically this is the right way to do it.
Yeah, if you're looking for the means, that's specifically what you're looking for.
Yes.
The means. If you're trying to make sure, looking at upper and lower bounds and trying to make sure it's within them, it's the variance you're looking for.
Yeah.
You'd definitely be looking for the variance.
Okay. Yes.
Like,
Sometimes you say mean should be this, and I don't want to have the variability be more than plus or minus 1 millimeter, for example.
yeah.
So you have two things. You have to define a confidence interval for the mean, plus a confidence interval for its variability at the same time.
Okay, yeah, and if you're doing both of those at the same time, how do you do that? Like
They're kind of two not really separated, but you have to do it individually. Yes.
Okay, so you do the mean, you make a test for the mean,
Yeah.
and then you test for the variance.
Yes.
And then
But usually it's just one of those point of interest, all right? If you have if the accuracy is important for you,
yeah.
it's based on the assumption the mean is kind of consistent, but it's just the variability is one of the things that we are emphasizing on. So, people usually go with one rather than both at the same time.
I think they made the assumption that variance was consistent.
Variance is consistent, okay.
Yeah,
That makes sense for you. Okay.
I was like, I didn't understand why they would do that. Why would you make that assumption that variance is consistent?
No.
When you're looking at upper and lower bounds and trying to make sure the width of the metal is within them, assuming metal on what basis would you assume variance is consistent?
I
That makes no sense to me.
Yeah, that's true.
It was frustrating.
I know.
So yesterday night at 2 I submitted to one.
So are you ready for your presentations on Monday, folks? Wednesday, my bad, okay. So, seems you're not ready though, for Monday, because you have plenty of time. So, yes. So that could be just one thing. For the lab, you probably need to record a video and send it to people because they may need it for their project. When is the deadline for the project?
Sunday.
I'm going to send it by Tuesday.
Lab. I can upload the lab by then.
Yeah. No, that's fine. I'm going to extend by Tuesday.
I can upload the file by then.
So we can upload the file, but if you can, we can also record a video and send it to them. Okay? How's that, folks?
That's much.
And also, the lowest grade on our labs, will that be waived?
Haven't decided yet. Yeah.
How
I don't
about
know.
lowest grade on our exam?
No, exam, no way. But assignments, yes. I'm not sure about the labs. I have to see how's the grade. Like, if it's pretty high, no. And this is not something that I say yes or no. I have to look at the grades now. But I don't want to, Nah, I shouldn't say that. But you assume it's no. Yeah.
So suppose I kind of like have something like this where I took kind of like a survey, and so 20% gave an answer of 100, 57% gave an answer of 50 or something like that. So these are the numbers, and then this is kind of the distribution. Is something like this what we would use if you want to like find out if our answer, if our population falls in here? How would we do that? Something like that. So this is from our sample, and we want to find out.
What are those numbers?
That's like the score.
The score of what?
Doesn't matter. It's like a test score. So like 20% got a test score of 100.
Okay, so this is a score based on 100. So you fit a distribution to it, and it says, for example, normal with the mean of 45 and a standard deviation of 2. You find the probability of x be less than something based on that normal distribution. Chapter 6, is that right?
Okay.
Does it make sense?
Yeah.
Okay, folks. So I don't want to talk about what is the two sample test. You know, we have two population, we are comparing two means together, and therefore we have to somehow, which one has a larger or lower, or we might also compare difference of means. For a two-tailed test, we have mu1 minus mu2 equal or not equal to 0, because we're testing differences. For the left-tailed test, we have mu1 less than mu2, and for the right-tailed test, we have what? Mu1 more than mu2. Why more than? Because I'm talking about the alternative, folks, H1. I'm talking about these symbols. Okay? So, depending on the type of the test, if I have known variance, I use Z. If I have unknown variance, I'm going to use T. And for the unknown case, we have assumption of equal or unequal variances. The same thing we had for the confidence interval. Let's start with the first one. If I have known variances from two populations, I'm going to run a test. I have x bar 1 minus x bar 2, the mean of samples, minus mu1 minus mu2 that you are testing, over sigma squared 1 over n1 plus sigma squared 2 over n2 square root. And that's your Z calc, and you're going to use Z distribution for this. So, we're going to go through another example for cars. You have two different types of cars, and we're comparing their MPG, miles per gallon. And my friend here is going to read the example for us.
Comparing the MPG of two cars, the 2004 Ford Expedition has a standard deviation for MPG of 0.64
miles per gallon.
In a sample of 40 tanks of gas, the average miles per gallon usage was 17. The 2000 Ford Explorer has a standard deviation for miles per gallon of 0.52 in a sample of 50 tanks of gas for the Explorer. The average MPG usage was 18.5. At alpha is equals to 0.05 significance level, is the true mean miles per gallon lower for the Ford Expedition?
Okay. So what we are doing here, we are testing two different means of two different populations. So I want you to go ahead and solve the problem. Ford Expedition. Bless you. So, I have two cars. X1, random variable of the miles per gallon for the Ford Expedition, X2 for Explorer. Unknown means, however, we know the standard deviations. Therefore, I'm using Z distribution. So, distributions are based on mu1 and mu2 are not known, but these two are known to us. First, I want to see whether the true mean of Expedition has a lower mean compared to the Explorer. So this is my concern. I put it into my alternative. I'm saying what? Mu1 is less than mu2, and mu1 more than mu2 goes to the top. Second step, a statistic, Z-calc. We did the data analysis, we got the data from each. We found that X bar 1 is 17 minus 18.5. This is X bar 1 minus X bar 2. Minus mu1 minus mu2. What's the difference that we are testing? I forgot to mention this, folks. I can rewrite this to I can rewrite the whole hypothesis like this. I can say I'm testing what? Mu1 minus mu2 more than 0. Mu1 minus mu2 what? Less than 0. Therefore, the difference that I'm testing is based on the value of 0. I'm saying they are different or not. I'm not saying is the Expedition has a better MPG at least 5 miles per gallon. My threshold for comparison is just 0. Therefore, in this test, mu1 minus mu2 that you are testing is 0. And that comes from the test. Over sigma 1 squared, 0.464 squared over n1. What's n1? Plus 0.52 squared over n2. What's n2? 50. Yes. Z-calc is?
Minus 11.99.
99. Thank you. I need more space. Do you mind if I remove those? Can I erase this? Okay. I put the third step on the top. This is a rejection region method. This is normal distribution. Z of 0. And this is a left, right, or two-tail. What's the type of the test here, folks?
Left.
A left-tail test. Why? Because this is a less than sign.
Yeah.
My area is to the left. Alpha of
0.05.
0.05. This is Z of 0.05 or negative 1.9. 6. Am I right? Now I make decision. My z is what? Negative 11.99. It's somewhere on the other side of the board, is that right? This is negative 1.9 something. 11 is somewhere here. Negative 11.99. All the way at the end of the rejection region, the best part of the rejection region. No evidence showing that there is a kind of acceptance region for us. So the conclusion is what? Z-calc falls in the rejection region. Therefore what we do? We reject the null. Meaning that what? Mu1 is less than mu2. Meaning what?
Code explanation has lower LPG.
So which one do you like better?
Code Explorer.
Explorer. MySQL gathering is larger, is that right? So we better go with this Explorer one. So look, a statistic also could help you to buy cars. And drink coffees from Dunkin' Donuts.
Trucks are generally,
And then print papers together, huh? What? What is it?
trucks are generally lower miles per gallon.
Yeah,
Anyway,
that's
they're more of a,
yeah,
they're hauling. The idea is to pull a lot of weight.
that's true.
So in the expedition there is only.
But you can also pile up a lot of stuff in your trunk with the expedition one.
True, but the truck is designed to like haul boats or like wood or something like that. There.
So, but we are not. If we are not hauling, so what's the point? So this is the MPG without hauling anything like.
Oh, it's true. I think they're designed to be less efficient.
But it's not that efficient. Like this is pretty like here. The p-value. Can you tell me what's the p-value even without using t-table? 1 to 3. Pretty quick. Tell me. What's the p-value of the test?
0.
Exactly. Why 0?
Here to the left of
3.99.
Okay.
It's 0, yeah.
A bonus point for you. You just came in, huh? So that's true. The p-value of the test is 0, 0, 0. Why? The area to the left of my z-calc is negative 11.99. Area to its left, almost nothing. So its p-value is 0. Again, 0 compared to alpha 0.05 is less than 0.05. We reject the test. Okay, does it make sense? Okay, great. For t-test, when sigma is unknown, for variances are unknown to us, we have two conditions. You are familiar with this. One equal, one unequal variances. In case of equal variances, we use the second equation. In case of unequal variances, we're going to use the third one. What's the difference? In case of equal variances, we have pool variance. You remember that SP?
Yeah.
But in terms of unequal, what we do not use the pool standard variance, but we have degrees of freedom equation like this. So you have to figure out which condition, in which situation you're having, and then find the right calc to use to find the test of hypotheses. Okay, so I'm just going to solve one of those for you guys in this example. This is the price of prescription in two states, Colorado versus Texas, and we're going to see in which state we pay less for drugs prescription. Okay, and my friend here going to read the example for us.
The price of the prescription drugs are on the ongoing national issue in the United States. Zocor is a common prescription cholesterol reducing drug prescribed for the people who are at the risk of heart disease. This table shows Zocor prices from randomly selected pharmacies in two states. Yeah, at alpha is equal to 0.05. Is there a difference in the mean of all the pharmacies in Colorado and Texas?
So I want you this side of the class work on Texas data. I want this side of the class to work on the Colorado data, telling the export and standard deviation of the data, and we solve the rest of that together. Again, in your problem, make the assumption of equal variances. Okay, is that clear, folks? For this example, we have equal variances and then solve the problem. So I define x1 and x2. Both of them have unknown mean and variances. Therefore, I'm using t distribution. So, what's the hypothesis, folks?
Two-tailed.
Why two-tailed? Why two-tailed?
Because it is written, is there a difference in the mean for all? So it should be equal.
I'm just testing this difference. I'm not saying whether Colorado is cheaper than Texas or not. Is that right? Is there a significant difference or not? Therefore, it's a two-tailed test. So I'm writing the hypothesis like this: mu1 minus equals to mu2, and mu1 is not equal to mu2, or mu1 minus mu2 equals 0 or not equal to 0. Either of those could work. So, from this side, I need your statistics. I want to say Colorado, Texas.
Colorado's mean is 133.99.
133. And S.
11.01.
N.
16.
Texas.
X bar 138.01.
S.
12.66.
N.
13.
13. So now I have to form my calc. I need to find SP. Is that right? What's SP? Pooled standard deviation, or SP squared is pooled variance. This is the equation for this. N1 minus 1 times S squared. Is that right? So I'm going to find SP squared. N1 minus 1, 15. Times S squared is 11.01 squared. Plus 13 minus 1, 12. Its variance 1266. Is that right? Divided by 16 plus 13 minus 2. So what's the SP squared?
Wait, sir. I don't have that. I mean, I have to calculate. $72.97.
Are you sure?
Yeah.
72?
0.97.
72.97. Now I can find my T calc. I'll write it here. T calc equals to x bar 1 minus x bar 2. 133.99 minus 138.01. This is x bar 1 minus x bar 2 minus difference of means, which is 0. I'm testing mu1 minus mu2 equals to 0. Is that right?
The SP is coming 138.5.
I have 138. But sir, I calculated this.
Okay. You still have to use your friend packet, my friend.
Square is missing, sir.
So,
That square is missing, that's why, sir.
yeah.
So 138.57.
138.57. Okay. I'm just going to stop here. Over the square root of 138.58 over N1 plus the same thing, 138.58 over N2. The answer is T calc.